Hello everyone, welcome to this video. In this video, we are going to learn about the state space model using OpenMathAI. So, let's get started. What is a state space model? A state space model is a dynamic mathematical model used to describe how a system changes over time. Unlike traditional regression models, which mainly predict the output directly from the current input values, a state space model uses internal system variables called states to represent the system's current condition. A state space model works using two main equations, the state equation and the output equation. The state equation calculates how the internal states change based on the previous states and current input values. The output equation then uses these internal states to calculate the predicted system output. During prediction, the model receives the current input values and combines them with the previous internal state. It first estimates the new state of the system and then uses that state to predict the output. This process is repeated at every time step, allowing the model to capture the dynamic behavior and memory of the system. We will use a DC motor dynamic dataset for the state space model. This dataset contains 1,200 sequential data samples. The input features are input voltage and load torque, and the target output is motor speed. The time column represents the order in which the measurements were recorded. During training, the state space model learns how the internal condition of the DC motor changes based on the previous motor state, input voltage, and load torque. It also learns how these hidden internal states produce the measured motor speed. Once the model is trained, OpenMathAI uses a learned state transition and output relationships to predict the motor speed for new sequential input values without retraining the model. So, let's get started. Open OpenMathAI. In this demonstration, we will use a DC motor dataset with the state space model. Click Create New Project. Enter the project name as DC Motor Prediction. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for Dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Configure the dataset by specifying the input features and output target. There is also a feature called Ignore, which can be used for columns that should not participate in model training. Select the input and output columns manually or use Smart Suggest for automatic recommendations. There is one more feature, Signal Diagnostics. There is a free columns. First one is column its tell which features on the dataset like inputs and outputs name. Second one is VIF if it tells how much correlation of the features. Third column is status if it's OK, moderate, high, redundant, and constant. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the state space model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Train Models. Review the training configuration, test data split, which determines a percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. And also another feature is added that is train from scratch or continue from use model. If you train this model before you use that option, modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R-squared measures how well the model explains a variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, root mean squared error, the square root of MSE. RMSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits the dataset. It is generally derived from tricks such as R-squared, RMSE, and residual errors. Model accuracy is commonly estimated using the R-squared value. Example, r squared equals 0.95 accuracy, almost equal to 95%. Click Fit to Window. You will see 3 types. Fit to Window, comfortable, compact. Then the Clear History. If you click that, it will clear the history before its trained model. Another is Deselect and select all trained model for export. Click View Curves. You will see the diagram of R-squared residuals and residuals diagram. Click Math and Code Preview. View the generated mathematical equation and source code. OpenMathAI provides expression of the data, detailed explanation of the expression, and an implementation code. Return to the result page and click Deploy Status. Click Export Model. Choose a required export format: ANSI, FMU 2.0, FMU 3.0, Verilog RTL, VHDL RTL, Python Bundle, ONNX Hub. You can choose any of these formats and export. You can also download the free trial versions of OpenMathAI and Twin Simulate. Thank you. Stay tuned for more OpenMathAI demonstration.